You've already been introduced to the concept of complex numbers in previous courses, and we looked at the idea of basic operations such as adding, subtracting, multiplying, and dividing them. And now that we've moved further into trigonometric concepts, we're going to use those to increase our understanding and use of complex numbers. One of the first things we're going to do is be able to put these complex numbers in a two-dimensional plane. We're going to use this as a way to visualize the complex numbers. As you know from your work with real numbers, we typically graph things with an X and Y value. Well, here we're going to use a complex plane in which we have a real axis and an imaginary axis. Here's our real axis, here's our imaginary axis. And if you remember, complex numbers are of the form a plus bi. The A piece will go on the real axis and the B piece will go on the imaginary axis. So for example, here we have the ordered pair 3, 1 represents the complex number 3 plus I. The ordered pair -1, -4 represents the complex number -1 minus 4i, and 4, 2 represents 4 minus 2i. Once we understand this idea of a complex number, which we can refer to z as the complex number a plus bi, we can then define what we call the magnitude, represented just like absolute value of the complex number. Note that the magnitude is nothing more than the distance that that complex number or that ordered pair is located from the origin 0, 0, just like absolute value is the distance that a number is located from 0 on the number line. Let's practice finding the magnitude. To find the magnitude of -2 plus 5i, we will take the square root of a squared plus the square root of b squared, which gives us the square root of 4 plus 25, or the square root of 29. Likewise for b, we're going to take the square root of 1 squared plus the square root of -3 squared, which gives us the square root of 1 plus 9, or the square root of 10. We can also use the concept of z to graph regions as opposed to just graphing points in the complex plane. Remember, this notation is read the set of all z. The line indicates such that the magnitude of z is less than or equal to 1. If you graph that, notice all of our z's, so all of these points that are shaded here, the magnitude or the distance they are from the origin is less than 1. It's a circle. Likewise, if we look at this example, z is equal to the complex number a plus bi, such that, that line here, the magnitude of z is less than or equal to 1. So we're going to have this radius still of 1, but the b's are all positive. Notice that keeps us above the real axis, giving us just a semicircle.